ahead and start this up again. I started a separate channel for this workshop on my YouTube account, so once we get all the way done, I will add better labels to each of the videos and post a link to this. So if any of you wants to hear any of this again, or if you have friends or colleagues who'd like to hear it, they are all welcome. So that is working. The schedule for today, same as yesterday. We'll stop around 10 for a break, hour and a half for lunch, beginning around 11:45, break in the afternoon, and then we'll see what we have the energy left to talk about by the end of the day and who's around. I had tentatively planned for cross-random effects models because those are becoming more and more popular for a lot of repeated measures designs, and so I wanted to tie those types of models into what we're talking about, but I'm also open to flexibility in that regard. So I'm assuming you just remember everything perfectly from yesterday and I can just pick up where I left off? Is that fair? Maybe not? Yeah. Some of you are like, yeah, of course I do. Well, for those of you whose coffee hasn't kicked in yet, and I am one of you, let's do a little review here. So we'll play Name That Tune, essentially, here. So I have some questions, and you have to tell me what goes in level 2 or level 1. So for the first question here, blank person as an adjective, what goes in level 2? I'll give you a multiple choice here. Between or within? This is between. Very good. And in the context of longitudinal data, it's between and within person, but it's always between and within something. So if I'm talking about kids in classes, it's between and within classes. If I'm talking about rats within litters, it's between and within litters. So you can always use these words between and within. What it modifies depends on the context of the study. So if you want to sound fancy, what kind of variability are we talking about? Inter or intra-individual at level 2? This is inter. Put that in caps. That means intra must be level 1. The letter to represent this source of variance in the equations that I'm using. Notation is always author-specific, but I'm trying to be internally consistent. What letter do I always use at level 2 to indicate some kind of variability? U, yes. So far, you know I'll put this in parentheses here, U0 or U1. But it's always U in my notation. And at level 1, E, yes. And some authors would use R there instead. That's also fine. Some authors use one of the Greek letters that I call squiggle. There's squiggle 1 and squiggle 2. Squiggle 2 is the one that has like an extra curly Q at the top. I never use squiggle because I can't draw it. So it's U because I can reliably draw that. The name for the type of variance given by the letter. So here I'm going for residuals or random effects. Which one of those is level 2? Random effects. So random effects is the umbrella term. Within that are specific subtypes of random effects, random intercepts, and random slopes. That means at the level 1 side, this must be residuals. Yes. The matrix. Where do my random effects variances and covariances live? What letter? G, very good. Where do the residual variances and covariances live? I heard it. R, very good. And when you put them all back together again, you get V. V for victory. I finally get this. If you want to tell, say, SAS or SPSS or Stata or any other mixed modeling package, what G should look like, what goes in it, and what kind of structure it has. Which statement allows you to do that? This one, it's random. Yeah, this is somewhat program specific. And this one is repeated. So I get lots of questions from SAS users about the difference between these two, but this is it. Random is used to refer to any kind of random effects. It is optional. If you don't write it, you don't get anything. So you have to write intercept. The distinction is in stata. Random intercept shows up by default when you do the bar ID part to differentiate levels. Repeated is always there by default. By default, you get an E-variance no matter what. And that E-variance has constant variance across all observations with no covariance by default. If you want something else, then you have to put a repeated specification to it. And this one then, the form of the matrix. This is where we're referring to type equals UN forever and ever, amen. Unstructured is what that means. That means that the random effects, variances, and covariances get to be whatever they feel like being. It makes no sense to put a structure on them. In contrast, the R matrix can be whatever you want it to be. This default structure where all the residuals have the same variance across observations and no covariance, that's a testable assumption. You might also need some kind of autoregressive or topolets or some other kind of residual correlation in addition to your random effects, but whether or not you need that is a likelihood ratio test. In theory, what the random effects are for is capturing whatever correlation there would have been among the level 1 residuals and sticking it over here in level 2G. But in intensive longitudinal data with lots and lots of observations, there may be more sources of correlation than just the random effects. And so it is appropriate to think about additional things you can put in the R matrix and to test them. Let's see. Anything on this list that I forgot in terms of vocabulary? Okay, so exceptions to this rule. So I just finished a brand new example in my advanced class for 3-level data where we have 4 observations per day, 20 days, 25 people. So this idea of between versus within in that kind of design is inadequate. In that kind of design, we would actually have level 3 would be between persons, and we have a potential level 2 in the middle. Make this a little bigger. So level 2 and level 1 is what I would call within persons, but that's both within days and between days. So level 2 is between days. Level 1 is within days. Without this distinction of between and within days, we would be assuming that all observations from the same person are equally related, regardless of which day they came from. If there's something specific about the day that causes an extra correlation, that's where we would introduce another kind of random intercept for the day level, in addition to the random intercept for the person level. As another kind of example, time is not necessarily always level 1. So a couple of my students have data across countries in which, good morning, we have different people surveyed each time they do the survey. So it's a longitudinal measurement of countries with a different sample at each occasion. In that case, people are level 1, nested in occasions at level 2, nested in countries at level 3. So if we have person-level outcomes, it's a 3-level model. If we have time-specific outcomes for countries, it's not a 3-level model because persons don't have anything to do. It's just a 2-level model. We'd have to aggregate the person information, bring it up to the time level to use that as a predictor. As a third example, time can be level 3. It's possible. I had another student who was looking at survey data where it was the same survey repeated several years in a row, but each time they did it, it was a different set of interviewers interviewing a different set of respondents. So it was respondents nested in interviewers, nested in occasions. And he called that a longitudinal study, and I'm like, not really. it's over time, but there's nothing that's being shared between occasions. So in that case, time is actually level 3. And depending on how many occasions you have, you might just want to put in a dummy code, set of dummy codes for which times it was, and not think of it as a level at all. So what levels you have, how many you have, and what to call them is always dictated by your sampling plan. This is just a basic case of a 2-level design, but this may not be sufficient for longitudinal data. So-called intensive longitudinal data, where you have multiple levels of within-person time, would represent multiple levels of a model. But in that case, we would still have the same vocabulary. Random effects would be in both level 2 and level 3. Residuals would be in level 1. Repeated would be used to structure any kind of residual correlation within days, whereas we would have 2 different random statements. Random for person ID, and then random for day here. So we talked about fixed versus random. Fixed means everybody gets the same, right? A fixed slope is shared by everyone. A fixed intercept is shared by everyone. In the same way that in regular old linear regression, your intercepts and slopes are shared by everyone. You just called them intercepts and slopes in regression because you didn't need another modifier. They were all fixed. There was no random that you needed to differentiate them, so you could just call them intercepts and slopes, but they were fixed effects. The new part that we're doing is adding random effects, allowing each of those fixed effects to vary over a higher level unit. So in this context, within person predictors such as time or anything else that varies over time can potentially have a random slope over level 2 people. More generally, lower level predictors can have random slopes over upper level units only. Fixed effects at the highest level of the model cannot have random slopes because they don't have a higher unit to be random over. So we'll talk more about that this morning. I had a couple questions from folks about their specific types of designs and the idea of within-person fluctuation and how time played into that. If you're interested in predicting differences in variability, so let me give you an example. If I collected mood ratings every day for a week, let's call it negative mood. Are some people more grumpy than others? What do you think? Let's be social psychologists today. Are some people more grumpy than others? That guy? Yeah. You've just been outed by your colleagues, sir. Captain Grumpy in the corner there. Are some days worse than others for everyone? Yeah. So one thing a model predicting mood can do is to try and figure out why some people are grumpier than others. That's level 2. That would be person-level information trying to capture why we have a random intercept. At level 1, we have why are you grumpier today than your own average? What happened today? That would be level 1 time-varying predictors trying to capture level 1 residual variance. But another kind of question you could ask is why are some people moodier than others? Where moodier refers to their own fluctuation. Some people are just sort of straight across the board, nothing flaps them, and other people are very reactive. None of what I just referred to captures that idea. That idea is in level 1 residual variance and whether or not each person needs their own of that. So level 1 residual variance captures deviations around your mean. These models by default assume that that is the same for everybody. In some contexts, such as growth modeling, that seems fairly reasonable. In context where your study is designed to capture differences in fluctuation, that's probably not going to be the case. People differ from each other in the extent to which they fluctuate. So if you're interested in predicting differences in moodiness, in consistency, in fluctuation, that is another type of extension to a multi-level model. I can send you this reference if you're interested, but this is my first and only quant psych graduate from the University of Nebraska, Ryan Walters. The program started when my husband joined me at the faculty, and it died when we moved. So this guy snuck in the middle, and I'm happy to say he graduated and he has a job at Creighton University. So this is his dissertation that is going to be out in multivariate behavioral research shortly. He was looking at these types of models in his dissertation, and this is a paper that's talking about how to do power analyses for these kinds of studies, but it also gives an overview of what these models are for. But there's a picture in here that I think is helpful in explaining this concept. So if you think about this as your sample mean and these fluctuations around it as sort of the average amount of fluctuation, like the average amount of inconsistency or moodiness, here's an example of somebody who is both higher than others in their mean but less variable. And here's somebody who is lower than others in their mean, but more variable. So to capture these two kinds of person differences, mean differences as well as fluctuation differences, we need two different kinds of random intercepts. The random intercept I talked about yesterday gives us this mean difference kind, and he has labeled this as a lowercase b right here. So this is how far off your mean the person mean is. That's the first kind of random intercept. The other one that is trickier to estimate, and you need either version 8 M+, Proc NL mixed, or a Don Hedeker's custom program, is a random intercept that goes inside the residual variance. So it allows individual differences in fluctuation that you can then predict with person-level information. And so this is what's known as a location scale model, where the location part is exactly what we did yesterday. The scale part is allowing not only random effects that differentiate individuals and their variability, but predictors of those differences in variability. So this is not a topic I would have gotten to on day 2 of an introductory workshop, but I had several points. It is possible to answer questions about differences in fluctuation. You just have to add additional terms to your model to do so. The default assumption is that everybody fluctuates the same. So I'll go back to the title of the paper here. So in case you want to jot that down, or I'd be happy to send it to you. These are the proofs. I think it should be out pretty soon. So any questions on that? Yes, sir? Uh-huh. So can I tell you the story behind that paper?
I love stories.
No, this is a true story, and I tell my students this, and I usually bring in a prop to tell this story. I don't have it, but I'll just tell you the story. So that paper in 2007, that was published in 2007, was written when I was a postdoc in 2005, and I had a researcher come to talk to me about multi-level, and she wanted to predict differences in variability. And I was like, well, surely we can do that somehow. I don't know how, but I'll get back to you. And I started digging through books, and in the SAS for Mixed Models book, it's Walt Stroop and a bunch of other people, Wolfinger and all those, I found in Chapter 8 this tiny little example using the local option in Proc Mixed that allows you to directly add predictors to the residual variance in Level 1. So it's in the repeated line. You have this local EXP option, and you stick your predictors in, and it predicts the log of the residual variance. Now, why the log? Because logs keep the actual predicted variance from going negative, because you can't have negative variance. So you predict the log instead to solve that problem. And I thought, why did I have to work so hard to figure this out? And there's so many people that were asking those kinds of questions around me at the time, I thought, well, this could be a little paper. So I wrote a little paper and I submitted it to this same journal. And it came back and they had all these questions and they wanted it to be a bigger paper. So it turned into a full-blown tutorial on how to use this method. And in the introduction, I was very careful to say, this is not new. And I listed articles from like 1987 that had done this in other contexts. And I just said, I haven't seen it in this particular within-person fluctuation context, so I wanted to do a little article. I have a SAS program that does it all that you can download, so I meant it as like a little tutorial. Since then, I get asked to review papers using that article where it says, like, I invented this method, like that's how it's cited. I'm like, well, since it was in SAS already, and the first use of it was in 1987, I'm pretty sure I didn't invent it because I was in 5th grade. I'm pretty smart in everything, but I'm not a prodigy, right? But the punchline to all of this story is that that article won the award for the journal for that year of the best article, and I got a trophy. And I was so happy about it until I realized a few years later that I'm 99% certain that that paper is wrong. It's wrong. I haven't actually done the single model that would confirm it because I really don't truly want to know. But I'm pretty sure it's wrong, because what I did is put in level 2 person-level predictors of the residual variance without putting in this random intercept that would allow first individual differences in the residual variability. So I thought of these differences in residual variability as fixed, meaning there would be no more differences after the predictors went in, and that is the exact same error as putting level 2 predictors into a regression model without a random intercept. It's the exact same parallel error. I didn't know any better in 2005, and I could give you a list of papers that I now know have errors in them because it was the best I knew at the time, and I've since grown. So yeah, please don't read that paper anymore. So yeah, that's the story. Read this one instead. And then in 10 years, I'll talk about how this is wrong and we should have done something else. It's true. It's a true story. Other questions on this topic or otherwise? Okay, so another conversation I had yesterday. Where is the gentleman here who was talking about depression, and you have the differences in, I know it's your lab, right? Differences in in-person interviews versus surveys? He's not here? Yeah, he said, well, as my advisor was asking about the piecewise models. So I thought that was a really interesting question, and I wanted to share it with you because I think it highlights the difference in thinking about sort of theoretical mechanism of what causes change versus just trying to approximate the pattern. No, it's not a put down, I swear. It's not a put down. Yeah, no, I'm going to draw it. So in this tech room where I have 17 monitors, I have no podium and I have no whiteboard that I can draw, but I do have paint. So this is how I draw. I got my first copy of paint in about 1987 or so, and I loved playing with it as a child, so I'm happy to get it back out. But he drew me a picture where this is depressive symptoms on the y-axis over time that looks something like this. And he was saying that you guys were thinking about some sort of piecewise model to try and approximate this. And I pressed him, and I'm like, what the hell happened here? Like, why did you break them again or something? And it turns out that here and here, they came into the lab to do like a 2-hour battery of stuff, and the survey was part of the 2-hour battery, whereas these other instances, they were doing it elsewhere? So there are lots of reasons why someone might give a different answer in person in a lab than on the phone or online. I have no idea what those reasons are. But to me, it seems like there's 2 different processes happening here. There's sort of depression as indexed by self-report, which does appear to be declining across the study, and there's depression as indexed by maybe more valid self-report. I don't know what you would call an in-study assessment. Rather than trying to approximate these shifts as due to time when they're actually due to differences in procedure, what I had recommended he do is to think about modeling time as if these aberrations weren't there. So this looks sort of quadratic-y, maybe exponentially, like the theoretical curve might go something like that, with a little bit more wiggle, of course. But then you could put in dummy codes for whether or not it was in person, and potentially allow 3 different dummy codes for the different within-person effects, and those would then create, they would map onto this difference between the trajectory and what you had. So you could almost think of this as a multivariate set of outcomes where you have in-person outcomes and you have out-of-person, is that a thing? Away-person outcomes. And you could even estimate potentially both fixed and random effects for this difference. So a fixed effect would be, why do people look so much more sad when they come into the lab? And a random effect would be, why do people differ in how much sadder they look when they come into the lab? And to the extent that you can find reasons to predict those differences, you might be able to tell what it is about the lab that is related to this difference in behavior. It's you. You made them sad, or maybe you made them honest, or maybe there's demand characteristics, or I don't know, right? I'm not actually a social psychologist. I just play one on TV. But in this case, it's like there's 2 different processes happening because of 2 different kinds of measurement. So I think it would be more useful to try and build a model that captures these processes rather than just to try and capture these aberrations, because these aberrations wouldn't have happened at these particular occasions if the in-time surveys were here. You'd see a bump here instead, for instance. So I just thought that was an interesting story and I wanted to share. Anything else you want to hear about, more about that I mentioned yesterday, or that you have questions about from yesterday? We'll go back over notation and the examples that we did and then move on. No? All right, well, bye-bye paint then. Bye-bye Ryan's dissertation. A lot of grad students in the room. You know the big secret about dissertations, right? There's only 2 kinds. Do you know this? Do you know what they are? Done and not done. That's it. You want the done kind. Now, there are lots of kinds of papers that come out of your dissertation, but you can be working on those when you're a happy postdoc or a happy professor and you're making like 4 times as much money. So done and not done is the goal. All right, so let's do a little bit of review then in terms of notation. Let's pick up in lecture 2. So we have, this is slide 5. We'll go back over this real quick. In any longitudinal data, the first thing you want to do is figure out how much variance you have of what kind. So in a simple, I will say simple longitudinal study where you have just a few occasions within a person, it's not, multiple days, multiple times, that kind of thing. We can think about having 2 different kinds of variability. U0I is the random intercept, the difference between people. This is level 2 random intercept variance, inter-individual mean differences. This is the part of the data that's cross-sectional, that would have been there had you measured them once. From there, the deviation of each person's occasion from their mean is level 1 residual variance, within-person variance, the extra part that you get from longitudinal designs. Empty model, then, in multi-level modeling notation. Things in red are fixed effects in the model for the means. They are predictors that are in the data set, and your job is to figure out what kind of fixed effects they have with respect to time to capture the average trajectory. So we switch from having the fixed effects and the random effects and everything in the same line in this notation to having them in different lines. Beta 0 I is a placeholder. It is just a way to represent the combination of the fixed and random intercept that creates each person's individual intercept. And this idea of fixed plus random gets to be what you have. That generalizes to every kind of level 1 effect. So gamma 0, 0 in this case, because we have no predictors, is the mean of the person means. U0I is how far off your mean is, positive or negative. You put those together, you get your mean, and then E picks up the difference between your mean and each subsequent occasion. So there's two parameters in the model for the variance, level 1 residual variance, level 2 random intercept variance. We do interclass correlation with these. Let's talk about that for a second. Interclass correlation is the proportion of variance that is within or between. It's between. Interclass correlation is the proportion of variance that's level 2 random or level 1 residual. Which one's between? It's level 2 random. Yep. So it's the sum of these two on the bottom, and the numerator is the random intercept variance. So it goes from 0 to 1, where 0 means no between information, all within. 1 means all between information, game over. You do not have a longitudinal study. Then we talked about fixed and random time. And these are linear effects, but the ideas apply to any kind of time effect. So the first case was no fixed time, no random. So the sample black line here is meant to convey the means across time. These are individual trajectories. So this is no fixed, no random, because there's no change, and everybody no change is the same. That's what this model predicts. The empty means random intercept model says that's what your data look like. Then we add stuff to it to see how much better we can get the model. Here's yes fixed time because people change, but everybody changes the same, so it's not random time. And then the bottom ones both show random effects of time because we have different slopes for different folks. The fixed effect is what the random effects are varying around, so we will keep it in the model even if it's not significant, such as would be the case in figure C here. Random effects are always phrased as how far off your slope is from the main slope, the fixed slope, so you have to keep the thing it's off from in the model. So here's the equation then to pick up fixed linear time. We have a beta 1 effect here, that level 1, that gets its own level 2 equation. We talked about pseudo R square. When you explain level 1 residual variance, only level 2 random intercept goes up. Then we add a random time slope. So each person gets their own U0. Each person gets their own U1. Each of these are phrased as deviations from the fixed effect. And because these two U's are common to a person, we are also simultaneously adding their covariance. And that shows up in the G matrix in the off diagonal. All right. Let me see. Did matrix stuff. I'll let you read more about that. I don't have the energy for that right now. I'm sorry. And then we looked at these same principles in example 2. So we started off with the answer key. So in example 2, the first model was saturated means, which is where you put time on the class statement, meaning that you make it a categorical predictor. You estimate as many parameters as you have occasions. So it's one fixed intercept plus a number of times minus one fixed differences. That gives you the answer key with respect to what your fixed effects of time are supposed to be doing. The answer key on the variance side is this idea of unstructured, where I'm not using any random effects. I'm not trying to pattern the variance and covariance over time. I'm just letting it be whatever it feels like being. That's type equals unstructured. So this model is H1 in SEM parlance. It's as good as it's going to get, and it is only possible when you have balanced data. Time can only be a categorical predictor when everybody's sharing the same set of times. And everybody has to share the same set of times for there to be one matrix that characterizes your whole sample like this. So this is the answer key for the model for the variance. We determined that the variances were shrinking over time. The correlations are still pretty high, but the observations closer together in time on the first off diagonal tend to be highest. Here are my fixed effects for the means. Here is my traditional omnibus ANOVA test for the main effect of time. So this is the same thing as a multivariate analysis of variance approach to repeated measures. Here's my picture. So this black line right here is my answer key. I have a couple different examples of how to approximate it. We are going to look at quadratics, and I showed you briefly piecewise models the other day. And there's another one that I recently added that's not in the book where I just take the log of time, and that works surprisingly well. So I have a slide about that towards the end here. And here's the same type of description of the variances, which shrink over time. So then we started with empty means, random intercept. So here's R. This is my residual variance at each occasion. No covariance whatsoever, because the only reason for a covariance is over here in G. And if you take this random intercept variance and just like stick it everywhere in here, you get to V. So that's the total data put back together again across levels. That's what it's actually predicting. And the interclass correlation then shows up in the correlation version of the matrix as 0.82. So the average correlation across time is 0.82. Here's what it's averaging over is up here in the answer key model. So if you take the average of all these correlations, it's 0.82. But you can tell that that's not necessarily right for any one pair. That example, by the way, is in Chapter 3. Then we added fixed linear time, noting two different versions of time. Session is categorical, is an ID variable. It organizes the R matrix. C1 session is continuous. It's a slope. It's a linear slope in this case. It's only on the model line. It's not on the random line. It's not after ID on theta, for instance, and so it's only fixed. So everybody changes the same according to this model. We can stare at this p-value, otherwise known as a Wald test, to tell that that fixed slope is significant. So that significance effect size is given to us by pseudo R square. So of the 18% of the residual variance that we had to begin with, we just captured 21% of that 18% by adding fixed time. We then added random time, which allows people to have their own slopes. And I want to pause here to make a point of a question that I talked about yesterday also, whether or not in these growth models you need to control for the previous occasion. If you think about this in sort of an autoregressive context, this R matrix right here has no residual relationships whatsoever. It says the residual variance is the same across time and there's no correlation at all, because all of the reasons for the correlation are now over here. They are specific to level 2. They are intercept differences and slope differences that caused the original correlations. When you put it back together again, here's the V matrix for the total combined prediction across levels. Here's the formulas for how that V matrix got constructed. Here's the correlation version of the matrix. So look at these correlations. They're pretty high, and they're pretty close to the original data, actually. They're not too far off. The random intercepts and slopes did all of that. That much correlation was accomplished without any kind of residual extra relationship. So when otherwise well-meaning people tell you in longitudinal models you have to control for the first occasion, I think what they're trying to say is you have to be able to induce a correlation between occasions. Tell them, no, that's what my random effects are doing, and they're doing it better. Because this is a different pattern than an autoregressive pattern. An autoregressive pattern assumes what's called stationarity, or equal variance across time. It assumes fixed change only. If your data have individual differences in change, an autoregressive pattern is not going to be sufficient. So this correlation matrix shows you just how well the random intercepts and slopes were able to create to mimic the correlations in the original data. And they did so while allowing the variance to shrink over time, just like in the original data too. So we do likelihood ratio tests to decide whether or not we keep random things. Chi-square difference of 42. Critical value is somewhere between 5.14 and 5.99, depending on how much you want to care about the mixture chi-square thing. Either way, it's significant. So we would say that helps the model. So yes, people do need their own slopes. And that was where we left off with that. I think the coffee just kicked in. I'm talking fast again. Questions? Yes. Yes, so you can do that too, absolutely. I have an example in Chapter 5 with a random linear model where I added two kinds of residual structures, and when I do this example for my regular class, I add that example too. It would be a question of taking this repeated line right here and switching it from VC, which means no structure, equal variances, to AR1, and do a likelihood ratio test to see if it made it better. So if anyone wants you to stick in residual things, here's your answer. Dear Reviewer 3, thank you for that excellent suggestion. However, model fit was not subsequently improved when implementing it. Therefore, we stuck to our own model, neener, neener. Yeah, it's always an empirical question whether you need extra stuff. And I also had a question, by the way, about parsimony in model fit. So we get these things in addition to -2 log likelihood, AIC and BIC, and like 17 versions of it across programs. I'm guessing this was someone's dissertation that thought AIC was not good enough or BIC wasn't good enough. These are meant to provide supplemental information. The formal hypothesis test is the likelihood ratio test. These things take into account the number of parameters for AIC and also for BIC sample size that it took to get there. So it is entirely possible that you can have a better fitting model, but these things go up instead of down, thinking, well, it's better, but it's not so much better given how many parameters it took to get it better. So in theory, these all converge onto the same answer. In practice, they do not. The problem with these is that they aren't referenced to any kind of statistical distribution. There's no way to say it needs to be 1 unit better or 2 units better. It's just smaller is better. So it's dissatisfying if you're trying to make a claim on that. But they do provide this additional information as part of your model fit indices. All right, other questions? So if we go back to our original picture, what we're trying to model, there are ways of testing absolute fit, given that these are balanced data. But a way that will always work is to stare at the picture and think, do you think linear is good enough? I don't think so. This looks a little bendy to me. So I'm going to add some bendy in the next section here. And the easiest way to make it bendy that everybody will appreciate but not necessarily understand is quadratic. So that's where I would like to start for today. So picking up on slide 31. So the full version of this example is in my fall class, CLDP 944. I go over, using these data, every single version of the bendy models that's in these slides. So if you want to see the full picture as well as how to test absolute fit, it's in that example. I didn't think I'd have time to do it, and I was right because I thought I was supposed to finish this yesterday, but that is available for you, including additional stuff that's not in the book that I've since learned after publishing the book. So let's see, let me skip ahead just a little bit here. So an easy thing to do to make a line bendy is to add polynomial terms of time. And this is very common. It's easy to do in every software package. If you want to make a line bendy, you can add time squared, and that creates a quadratic trend. Time cubed creates a cubic trend. So a linear model assumes constant change. The line keeps going forever and ever. A quadratic model assumes that the rate of change changes. A cubic model is a change in how the rate of change changes, and so on. I have never seen anything past cubic make any kind of sense. If you have to go past cubic, you need to do something different. That's my thought. In terms of balanced time, you need number of occasions minus 1 to fit this number of slopes. So if you want to try to fit a fixed quadratic, you need 3 occasions. A fixed cubic takes 4. But if you think about the idea of what you're doing then, if I have 3 occasions and I fit a fixed quadratic, that is, here's my 3 occasions: fixed intercept, fixed linear, fixed quadratic. I may as well have just had my 3 occasions in the model because I've just repeated the information. I've just rearranged the 3 means into 3 parameters. So it's not really a summary. It's going to fit perfectly. The n-1 rule can be broken in unbalanced data because then what you're trying to do is capture the overall trajectory across people where not everyone would have contributed to every single data point. What to do with a quadratic is often a source of confusion, and I want to make it stop. I have read things in books that say, like, well, quadratics are just too hard to interpret. No, they're not. There are only 4 kinds. Because a quadratic term is essentially a two-way interaction of time by time, there are only 4 kinds. A quadratic takes the main effect of time and it makes it more positive, less positive, more negative, or less negative. That's it. You just got to figure out which one you're at. So the only trick that you have to remember is when you're looking at a quadratic coefficient, to talk about what it does to the main effect of time, you have to multiply it by 2. And I can give you 3 different reasons, and hopefully one of these will satisfy you as to why this is. So for example, if I have a fixed linear time slope in the model, because time now interacts with time, that linear time slope is specific to time 0. So if my linear time slope is 4 at time 0 and I add a quadratic time slope, then at time 0, the linear rate of change is 4. At that 1 unit in time later, it will be more positive by twice this quadratic. And because this, so one reason here for anyone who remembers calculus, I'm not among you, but I remember at least this much, what we're actually talking about is the second derivative of with respect to time. The quadratic coefficient itself is half the rate of acceleration. So when you take the first derivative, this 2 comes down to multiply the t, and it ends up being twice. So yes, there's always people that are like, yep, got it. The rest of you are like, yeah, no. If you're in that latter case, I'll explain it a different way, in the logic of interaction terms. So within this box here is a traditional interaction term between x and z, say in regression. This x by z interaction does 2 different things in this model. It takes the main effect of x and it modifies it as a function of z, and it takes the main effect of z, where's my little pointer, and it modifies it as a function of x. So it does 2 things. It shows up twice. But in my model, it's like I'm missing where z would be. I don't have the other main effect. But the interaction term still has to do something twice, so it does what it was going to do to the other main effect again to time. And if that doesn't make you happy, my third reason is because. It's the same reason I tell my son after he's asked why for the 17th time. Just because, Huey, because. Because I said so. Twice the quadratic is how the linear slope changes per unit time. That's the end. So to describe those things then, here's some different pictures. So this is slide 37. The first corner here is what I would call an accelerating positive function. I've once got into a debate with someone who is a physics major about my use of the term accelerating or decelerating. So if you don't like that, you can say more up over time. So at time 0 here, so I have tiny little slopes drawn in here that are supposed to represent the instantaneous linear slopes. It's the slope of the tangent line to the curve at this point. That's how we're supposed to talk about it, as instantaneous, because these slopes are not from time 0 to time 1. It's at time 0, literally. At time 0, the slope is 4. When I pair that positive linear slope with a positive quadratic coefficient of 0.3, 1 unit in time, it's more positive by twice the quadratic, more positive by twice the quadratic, more positive, and so on. So I think of this as accelerated growth. That's what I would call it. Over here is what happens when you pair a positive linear slope with a negative quadratic slope. Less positive growth. More coffee. Less up over time. So we start out at 4, but now the slope becomes less positive by 0.6 at each occasion. So you can't tell what the quadratic is doing based on its sign. You have to pair it with the linear to figure it out. In general, if you see a quadratic and a linear slope of opposite signs, it's less something. It's either less up or less down. If they're of the same sign, it's either more up or more down. So here's an example of another opposite sign. Here's a negative slope that's going less down over time. I would call this decelerating negative, but less down is maybe more correct. So -4 at time 0, it becomes less negative by the positive quadratic coefficient times 2. And then finally, this is a more negative. Accelerated decline is what I would call this. And the slope becomes more negative by 0.6 per unit time. So the instantaneous part, it's important to remember that when you're looking at a linear coefficient, it's always specific to time 0. So it's going to be different in a model that has linear only than a model that has linear and quadratic. And this curve right here illustrates why we would always keep the fixed linear in the model, even if it's not significant. Had we centered time out here, we could end up with a positive slope that's actually not different than 0. But having the quadratic effect too means that that slope has to change over time. It changes in a constant way, so it would be something else at a different point in time. And you can use estimate statements to ask for what the slope would be at any point in time from the same model. Now this picture also illustrates why some people may not like quadratic functions. Quadratics are easy. They work well to make a small number of occasions bendy. But let's think about this in the context of what kind of data would generate this. Let's say that this is some kind of academic achievement on a test that has a ceiling. Students get better over time. They get better as time goes on. They're learning. Yay, school. What does this model predict is going to happen if we keep measuring them? Yeah, all except gestures. They're supposed to get dumber. That's what the model says is going to happen if you keep measuring them. Now, maybe they hate your test and they give up and they start making shapes on your bubble sheets or something, but that's a whole separate phenomenon. So this model is theoretically not appealing for data where performance or growth or decline is eventually going to level out, either because of a measurement issue or just because of the phenomenon. The quadratic model predicts that what goes up must come down, and what goes down must come up. And for that reason, it can be theoretically dissatisfying. But it's common and it's easy, and that's why I think it's the most used. So I'll show you some pictures of what to do instead here, if you'd like to see those first. Questions on what to do with quadratics? Okay, well, let's look at this. Let's look at some pictures here. Let me skip ahead towards the end. So the very last slides show other alternatives to bendy that might be more satisfying. This is slide 56. So this is an example of response time data within one of the sessions that we're currently analyzing in our example. So what I was calling like session 1 RT is actually the mean across a whole bunch of trials. That's what tends to happen in experimental designs with response time. There's no reason why you have to create a mean per session. You could actually model the individual trial level data. That would create a 3-level model of trials within sessions within persons. Because as you can see, there's some learning going on here at the trial level. People get faster as the task goes on. So the observed means here are the very bouncy line here. This is the observed means. These are not like cleaned for outliers or any of that kind of stuff, so it's just this is the data. And I have the fits for 3 different kinds of models here. The red line is a quadratic. So you can see that it captures the bend, but it also predicts that if we kept testing them, they'd slow down again. The latent 2-piece, I had a question about this yesterday. That one's for you. I made NL mixed and SAS fit this as a latent 2-piece model, and it decided that the breakpoint was at like session 6, almost 7. And so it fit one slope for this sharp decline and then a slope that was basically flat for the rest of the time. Yes? Yep. Yes. I think that would be fair to say. Quadratic is a continuous change model. It's not that you can look at the end of the function and say that's where the quadratic is. The quadratic operates the whole time and paired with the linear to create this continuous shape. Whereas this is really like there's early practice and there's late practice. Like I'd have to come up with names for this to make sense. And in certain kinds of designs, that's easy. I once had a student who did research on infants and reactivity, and she had this study where she purposefully made her babies mad. And seriously, like she would bring the baby in and like let them play with stuff and measure their cortisol and amylase, and then she took their toys away, or she'd like hold their arms down and like piss them off, and they got like ah! And so they freaked out, and then they brought the toy back, or they brought mom back and calmed them down. And so she had a pattern that looked like this. And she called the first slope reactivity, and she called the second slope recovery. Now, I'll buy that, but she wanted to fit random slopes. And it turns out with only 3 occasions, she could either have this one random or that one, but not both. Can't have 2 random slopes with 3 occasions. We even talked about that, but you can't. So it would have been far better to create midpoint observations during freakout and during recovery so that you could isolate each slope with more precision. But yeah, you got to come up with words. Whether those are manufactured for the sake of publication or whether they reflect, true things, yeah, the implication is that these are 2 different processes. So the piecewise model is trying to capture what a truly nonlinear model might do a little bit better. So this blue line right here is the fit of what's called a negative exponential curve. And I talk about this in the book, and this took proc NL mix to fit as well. You can fit this in M+ through model constraints if you have balanced data. I tried to do that in my Chapter 6 examples, but that's the blue line. What separates this kind of model from the others is that one of the parameters is an asymptote. It explicitly has a parameter by which change is supposed to shut off at that lower level, or you can go up, like an upper level for an asymptote. So for processes that have an ending, like you're not going to keep changing forever, models that include asymptotes are going to be more reasonable. Unfortunately, they're harder to estimate, particularly for random effects. So the negative exponential here has 3 parameters. There is the nonlinear part, so there's an e to the function that has a rate in it. That is basically, hey, come back, how steep the decline is here, like how fast they come down, which is usually thought of as an index of learning. There is another parameter that you can either think of as an intercept or as an amount of change that is like the total amount they had to come down to get to their asymptote. And then where they end up at optimal levels is the asymptote. And so you can predict, like if they were given infinite practice, what's the best the model thinks they could do, and individual differences in that. So if you have processes that shut off like this, exponential models can be a good theoretical alternative. That being said, they're very hard to put in software. So here's a trick. And this isn't in the book, and if I ever do a revision of it, it's going to be log time. Take your time variable and take the natural log of it. Then you can use it in any mixed model package, any SEM package, and it creates something that looks an awful lot like an exponential. So on the bottom here, I have the log transform time as the x-axis. And so you can see the black line here is if there's purely a linear effect of log time, so here's the linear slope. When you unlog time and plot it against the original time variable, it creates this black line here. Let me get my pointer. Right here. So that's if there's no quadratic. If you add a quadratic and the data are trying to shut off change, a negative quadratic effect of log time creates this pattern right here. And that looks an awful lot like an asymptote to me. It would take forever for this curve to come back down, although it eventually would. So I like this as a reasonable alternative to exponential models if you run into difficulties fitting them. Just log time and fit a linear effect of it or a quadratic effect of it, same as usual. And this model actually fits the best out of any that I tried for this particular data. So Singer and Willa in their book have an example of log time, and I should have stolen it and put it in. But hindsight is 20/20. So I do want to finish this little example because we're going to use it this afternoon or later this morning actually, to add predictors. And thinking that we wouldn't get much further than this, I made the predictor example use quadratics because they're common and because they have their own idiosyncrasies. All of the idiosyncrasies would be the same if we're creating original time as a quadratic term or log time as a quadratic term. So it's the same problems, either one. So if you wouldn't mind, before we go to break here, I'm on page 7. Model 3A is adding a fixed quadratic effect of time. So at this point, the model has 3 piles of variance in it. At level 1, there's still E. Why are you off your line today? U0 at level 2 between persons is why did you start out so much faster than everybody else? And level 2 between persons is in the linear slope. Why are you changing faster than everybody else or less fast? And now we're picking up this effect of beta 2 right here, which is the quadratic effect of session, and we're giving it only a fixed effect. So we're seeing if making the line bendy and a common amount of bendy can better capture some of this level 1 residual variance. Why are you off your line? Well, because we need a bendy line instead of a straight line. So because we're adding a fixed effect, we can talk about actual reductions in variance. Because we're adding the effect of a level 1 predictor specifically, the reduction in variance should come from the level 1 residual, the same as with linear time. So you can define interactions on the fly. So I have C1 session star C1 session. In Stata, of course, we have our friend the pound sign, hashtag. Same model for the variance, and so R, G, and V have the same structure to it, just with less variance at level 1 than before. How R, G, and V get built is from those 4 numbers. So you don't actually need to print all of this stuff, but I think it's helpful to understand what the model is actually doing in creating the predictions for you. Here's my fixed effects. Because this is a fixed effect, I can stare at the p-value for it and declare it significant or not. So now the intercept is still the predicted response time at session 1, but now it's as predicted from a bendy line. So before it was 1900 milliseconds, now it's 1945. Before, the linear slope was minus 52. That was on average across time from a linear model. Now this linear slope is conditional. So there's language that goes with this that I want to review for you very briefly here. When I talk about main effects of predictors, I'm going to talk about them as belonging to one of two categories, and you can pick any of these synonyms. In experimental design lingo or ANOVA lingo, we talk about main effects versus simple effects. A main effect means it's for everybody. A simple effect is specifically for some value of a covariate, which is what happens when you have an interaction term. Another way of thinking about it is that the effective time is conditional. It's specific as opposed to marginal, which is for everybody. So in a linear-only model, the main effective time is marginal. Everybody gets the same predicted fixed effective time at every occasion. There's random variance around it. That's part of the model for the variance. It's unconditional. So once we add the quadratic, the linear effective time falls into this category because we have to say it's the linear effective time at time 0 specifically. It's conditional. You can also think of it as a simple slope as part of an interaction term. So this minus 120, given this interaction with itself, this minus 120 is the slope at time 0. It's the slope of the line tangent to the curve at time 0. Instantaneous would be the terms from physics lingo. Now if we look at the combination here, this is a negative linear paired with a positive quadratic. So which pattern is this? What does the quadratic do? Is it more positive, less positive, more negative, or less negative? It's a less negative. So the linear slope is initially significantly negative. It becomes less negative by how much, and don't say 13, per unit time? 26-ish, yes, twice. That's the trick. The linear slope becomes less negative by twice the quadratic coefficient per unit time. And that's written down there for you, by the way. Most of what I have to say is written. In the next model, I'll show you an example of how to get what the linear slope would be at any occasion. Here's my pseudo R-square. Because quadratic time is a level 1 effect, it should have captured level 1 residual variance, and indeed it did. So relative to the residual variance that I had before, I've captured another 6% of it by adding a common bendy line. Because residual went down, random intercept went up. The random effects went back up. Total R-square, then, is something that we can also compute. So in the code before, in SAS, there's an out PM statement that creates predicted outcomes from the fixed effects and saves them as a column to this new data set. In SPSS, the analog is this fixed pred time. Pred time shows up as a column in the current data set. And in Stata, it is this predict pred time shows up as a column in the current data set. So pred time is a new variable that is the predicted response time just from the linear and quadratic fixed effects of time. I then ask for a correlation between pred time, or in the pred time data set, between the variable that saves the predicted values and the original one. That correlation is 0.19. 0.19 squared is 0.04. So in total, change over time, linear and quadratic change over time, captured 4% of the variance in response time in this longitudinal study. Not a whole lot. But that shouldn't be too surprising that this is such a small number, because this was foreshadowed at the very beginning of this series by the empty model, in which we found out that 82% of the variance from the interclass correlation was between persons. So there was only 18% of the total information that was over time anyway. It's not too surprising that our overall R-square for the model isn't good, because the best we could have done is an R-square of 18%. If we got all of it, right? We got 4% instead. 4% in total. All right. So last model then, do people need their own bendy lines? Add the random quadratic. So picking up U2 here on the quadratic line. Here's an example of how to ask for what the model predicts the response time to be at any occasion. So intercept is the same thing as predicted outcome is the same thing as conditional mean. The model gives us the intercept at session 1 directly as a model parameter, but it also predicts what it would have been at any other occasion. Likewise, the model gives us what the linear slope was at time 0, session 1, but it also predicts what it would have been at any other occasion. So these codes here, the way to interpret these is because it's twice the quadratic, what we do to figure out what the linear slope is at each occasion is say what occasion is it and then multiply by 2. So this would have been time 0, time 1, time 2, time 3, time 4, time 5. Each of those numbers multiplied by 2 is how we create these values here. And the same sort of code here in SPSS. In Stata, we don't have to write so much. They have this lovely margins thing that allows you to do it across a range of values. So they win on that. dy dx is how to get simple effects out of Stata. So now my G matrix has 3 by 3 here. Random intercept, random linear slope, random quadratic slope. Because I have 3 things on my random line now, to do a model comparison to see if I made this better, it's degrees of freedom 3. Always the number of things on the line, because we have added random quadratic slope variance plus its covariance with the stuff that was already on the line. Still, the R matrix has no pattern to it. So we're still using just the random effects. Here's the V matrix that the model builds. Here's how it got there. That was some fun algebra. There's the correlation matrix. And here's my likelihood ratio test. Chi-square difference of 38 on 3 degrees of freedom. Yes, it helps the model. So I have a note here that we will not be calculating pseudo R square because we have not explained any more variance by adding a random effect. Random effects make new piles. They didn't explain anything. What we did is take what we used to call residual variance, why are you off your line today, and say, well, is it because you need your own bendy line? Yes, it is. Model fit improved when we give each person their own bendy. So now there's 3 ways that people differ from each other, in how they start, in how they change initially, and in how they decelerate over time. So to describe that in more useful terms, here are my random effects confidence intervals. We talked about those yesterday. The middle of each of these is the fixed effect, and then we take 2 standard deviations around it for the square root of each variance term. So the intercept then, if you take into account the fixed intercept plus the random variance around it, that comes from my G matrix, first diagonal, first row 1, column 1 of the diagonal. The intercept for the expected response time at session 1 on average is about 2 seconds, but across people it's anywhere from 900 milliseconds to almost 3 seconds. That's a lot of variance. Same thing with the linear slope. On average, people are significantly declining as evaluated at the first session, but that rate of change can be anywhere from a big decline, minus 400 milliseconds, to a positive number. Some people actually get worse at first. And I went back and looked at that, and I'm like, did I do the math? And then I found the spaghetti plot, and yeah, you can see it. There's some people that get worse at first, for whatever reason. So what if reviewer 3 sees this confidence interval and says, wait a minute, your fixed slope isn't significant because this overlaps 0? What do you tell them? Scholars in the back, what do you tell them? I'm going to call on you guys because you have the most experience in dealing with reviewer 3. Dear reviewer 3, I'll start you off. We apologize for being unclear.
We apologize for being unclear. This is more like a standard deviation.
Yes, very good. This is more like a standard deviation around the point estimate, describing the sample rather than describing the precision of the fixed effect. Exactly.
We submitted a manuscript to a different journal.
Well, this is an easy one to fix, right? I don't know if that would merit, dumping the journal, but yes, that's exactly right. It's not your typical confidence interval. It's not about how precise this slope estimate is. It's about how variable your people are around it. And so the same thing with the quadratic. On average, it's positive, meaning that the linear is slowing down, less negative over time, but at the individual level, you have all different patterns of accelerating change or decelerating change. So here are the results of the estimate statements. This is what the model predicts at each session. So this is the fixed effect predicted intercepts at each session. Here's the linear slope. So I find this helpful to describe what the quadratic is doing. And so first you can see that the math works. Each of these numbers, this is the slope at time 0, this is the slope at time 1, and so on, is different by about 26. It is becoming less negative by about 26 over time. And you can see the consequences of the quadratic. It eventually is going to start becoming positive. It predicts that people would slow down if you follow them long enough. And in fact, that's what I have in this picture here to illustrate this. The dotted line shows the prediction of the quadratic model if we were to continue the study out a few more sessions. They start slowing down again. The linear model says they keep going forever. The other piece of information that this might be useful for future planning, let's say that our purpose was to give them enough practice, but not so much that they get bored. Just enough. How many sessions does this output suggest would be useful? Are they changing at session 1? Yes. Session 2? Session 3? Session 4? Session 5? Yeah, somewhere between 4 and 5, they're done, on average. Now that's average, that's not to say individual trajectories. But on average, it looks like change is pretty well done somewhere between 4 and 5. So in addition to saying that you have a significant quadratic and that it captured this much variance, you might also try to put it in context. For example, there was a significant negative decline of sessions 1 through 4 that became non-significantly negative or even positive at sessions 5 through 6. That might be another sentence you could add to try and color what you're showing. So then in terms of prediction, here's how these models compare. So on the left is the model for the means. These are the observed means in black. The empty model is the straight line. That clearly doesn't work. The linear model is right here. That clearly doesn't work. Here's my quadratic model that does a pretty good job, although it's a little bit off down here. On the variance side, the variance at each occasion is what's on the y-axis. This is what is predicted by the V matrix for the total variance at each occasion. The heavy black line is the data. Here's random intercept only, which is constant variance over time. That doesn't work. The random linear is the one with the triangles. So you can see this, when you fit a random linear time slope, what you're saying is that the variance changes parabolically, quadratically over time. There's going to be some point at which it's at a minimum, and then it's going to get bigger again. And in the book, I think I have a formula to figure out when it's at its minimum, if that's something you ever wanted to know. In contrast, here's what the quadratic says should happen. It goes crazy. I actually had to cut off the y-axis. The top point is like clear up here. So quadratic fits better, but again, it's of questionable utility in thinking about prediction beyond just the data at hand. Now, in terms of whether this is good enough, it turns out that you can do a test of absolute fit if you switch to maximum likelihood. So this is a distinction that we haven't talked about yet, but in REML, you cannot compare models that differ in fixed effects with likelihood ratio tests. It's not valid. REML is based on the residuals, and the residuals are defined differently for each new set of fixed effects. But if you switch to maximum likelihood and you compare this chosen model against the first model, the answer key, the H1 saturated model, it actually doesn't fit. But in the world of polynomials, adding cubic or something like that is not likely to be more helpful. So that was where I ended up changing gears and working with piecewise models, which do fit, and log time models, which also do fit. The exponential models did not fit as well. So that's the end of that story. And the write-up for this is going to be in the book, so you can use that as an example of how to talk about this stuff in practice. So, any questions on that? Sir? Years. Well, so the book was finished in 2014, so it was 2009 when I started it. I had been playing with this data as a postdoc in 2004 and 2005, and I came up with the 3 alternative models for the data during that time. Since then, I've come up with log time, and there's probably some other ones. So I'm actually not done yet figuring out these data. That would be my answer. So 13 years later, roughly 14 years later, I don't think I'm done yet. So, other questions? Yes?
So in this example, it seems that the main question is like of interest is like the difference between sessions.
Mm-hmm.
I think you mentioned about like the trial differences.
Mm-hmm.
So it's like you're not really interested in how each trial differ between like people or whatever. Like does it still make sense to put that consider that as a different level?
If you're not interested, that's one thing, but one might argue that you should have been, because there's 2 different types of learning that's happening. Within a session, people are improving, and they're also improving between sessions. And so if you're really interested in characterizing individual differences in learning, why wouldn't you want to model both, given that you have the data for both? There's a sense in which the mean across sessions is probably misleading, because you're combining people who don't learn at all but are reasonably fast from people who start out really slow but learn a lot. So there's not a statistical reason, but it seems like you're wasting data. But I didn't want to do a 3-level model for my very first example. So, yeah. Other questions? All right, well, it is our first break then, so let's take 20 minutes and unthaw, and then we'll come back.